Good morning students. Today we are doing one galvanometer experiment and we are converting a galvanometer into voltmeter. So we already have the figure of merit given for the particular galvanometer and also the resistance of the galvanometer is also given. So I have selected galvanometer this one, okay. So this has got figure of merit 1.87 into 10 raised to minus 5 ampere per division and resistance chosen is 129 ohm. So let's see the rough circuit diagram how we convert a galvanometer into voltmeter. When I connect a galvanometer in series with a very high resistance, then this component becomes a voltmeter. So we will be first designing our voltmeter. So let's select the voltmeter should be measuring 6 volt. I am designing galvanometer into voltmeter to measure the 6 volt. So what is given to us? The figure of merit. Figure of merit is called as the amount of current required for a galvanometer to produce a unit deflection in the galvanometer. So the general purpose, the galvanometer has got the 30 divisions. So the maximum current measured by the galvanometer becomes 30 into the figure of merit. So I get this particular value 56.1 into 10 raised to minus 5, okay, multiplying the 30 and the figure of merit. And we know the conversion. For the conversion we have a formula, the R equal to V upon Ig minus G, and the V is 6 volt. I am designing for 6 volt. You can choose any other value also, okay, but I have a voltmeter which is in that particular range, so that is why I have taken 6 volt. So 6 divided by the Ig value, maximum current measured by the galvanometer, minus the capital G is your 129, that is the resistance of the galvanometer. So I got what? 10,566 ohm. So that means this resistance should be connected in series to the galvanometer. Then my device will become a voltmeter to measure the galvanometer, to measure 6 volt. Okay. So now let's see over here the verification circuit diagram. So this is this galvanometer and the resistance which is connected in series is the designed voltmeter. This is my designed voltmeter. So what I will do is I'll make a verification circuit. So I'll connect a standard voltmeter parallel to this designed voltmeter, and using a rheostat and a battery I'll make this arrangement, and this arrangement is called as my potential divider arrangement. So when I change the potential over here, when I change the rheostat over there, then potential across the rheostat will change. That will be read by these two. Okay, that will be read by these two, the design voltmeter and the standard voltmeter. So we have this observation table also that we need to fill up. Now I'll tell you how to make this circuit diagram and how to take the readings. But before making the circuit diagram, all these calculations should be done properly. Okay. Now see, I'll be making this circuit diagram, how to verify the designed voltmeter with the standard voltmeter. So we have a battery plus terminal is going to the plus of the voltmeter and negative is going to the negative of voltmeter and with the rheostat. So this is my rheostat, this is my resistance box, and this is the voltmeter, and this is the galvanometer, and this is my battery eliminator. So first I'll make the circuit diagram. See, the positive terminal of a battery is positive terminal of a battery is going to rheostat, it is going to positive of a voltmeter, and it is going to what? The galvanometer. So there are 1, 2 and 3 connections. So I'll connect 3 wires from this particular point. So now I connected this positive terminal into 3 wires. Now one is going to the rheostat. These two are called as the fixed ends of the rheostat. So these are this one and this one is the fixed end of the rheostat. This leg, okay, this connection is called as this variable point. So this is the one which is the variable point. First I'll connect these two fixed ends of the rheostat. So first the positive terminal will go to the rheostat, then it is going to the positive terminal of a voltmeter, see this is the positive terminal of a voltmeter, and then the last one is going to the galvanometer. So this is the galvanometer. This is the galvanometer. Now I have connected this part of the circuit. Now let me connect the negative part of the circuit. Negative part is going to the rheostat only, the other fixed end of the rheostat. So the other fixed end of the rheostat is this one. And remember, while making the circuit, okay, the circuit connection should be tight. And then the fixed end of this one is going to the fixed end. This is the fixed end of, the variable point. This is this point. This is the variable point that is going to negative of a voltmeter, that is going to the resistance box in series with galvanometer. So first I'll connect the galvanometer that is forming in series connection with the resistance box, and then the resistance box is going to the variable point and negative is going to the variable point. So this is connected to the voltmeter and that is going to the variable point of the rheostat. So this is the rheostat variable point. See, this is the variable point. This variable point is connected to the voltmeter negative, and then the resistance box. See over here, this is connected to the resistance box. Now, from this resistance box, how much value we have to take out? 10,566. So this is 10,000. See, this is, I have taken out the 10,000 and this is 500 and I need to take out 566. 566. This is 50. This is 60. 5. See, this is 10,500 and this is 50, 10, 60, 5 and 6. So 10,566 I have taken out and just tighten all the keys properly. Okay, there are chances that these keys are loose and then it will create error in your readings. So now my circuit is complete. Now let me switch on the circuit. Okay, but before that, just remember what is the least count of my designed voltmeter. I am designing for 6 volt, but the galvanometer has got total 30 divisions. So that means what? 6 divided by 30, that is 0.2 volt. It means when I get a pointer of the galvanometer, pointing at one division, it means that that is the coinciding division. That means 1 means what? 1 into the least count, that is 1 into 0.2, that is a 0.2 volt. Okay. Now I'll show you how to take the reading. Okay, switch on the circuit and then this is my rheostat. With the help of rheostat, okay, moving this section, you just see that first of all, just see the galvanometer deflection. So now right now see this galvanometer is nearly to 10 centimeter. This the galvanometer division, it is right now is 10 division, and then you know that the coinciding division in the galvanometer is 10. So this is 10 into the least count, that is 0.2 is what this is your 2 volt. But now let's see what is the standard voltmeter is reading. This is my standard voltmeter reading. This is also nearly to 2 volt only. So the error is what? 0%. Now once again I'll move this the rheostat and fix it up. Now this is nearly 15. So 15 into this 0.2 is my 3 volt. Now let's see what is my voltmeter reading. So voltmeter reading is also, now I think it is showing 3.2. So there is a small error in the reading. So I'll just repeat one more reading. So you have to design this way and then slowly remove this rheostat slowly. Okay, so now this is nearly to 20, and 20 corresponds to 20 into 20 or 0.2 is it's 4 volt. Okay, so and let's see what is my standard voltmeter reading. It's reading now 4.2, so that means there is small error. So now this is the reading by the design voltmeter, and this is the reading of the standard voltmeter, and you can calculate the percentage error in this. Okay, yeah, thank you.